Great, so the last step is to actually put these tools to work in an actual problem. Oftentimes when we talk about motion and velocity and acceleration, the calculus exam or textbook will talk about particles, and that's just imagine something small that's moving, and they're really just trying to get you to think about the situation. So a particle moves along a line so that its position at any time t is greater than 0. Why do they say that? Right, they're just telling you that time has to be positive. That's not really a very important piece of information. They're just reminding you that we're only talking about positive t's. So the position is given by the function, and then they give you this function. What are the inputs and outputs of this function? Exactly, so the output is the position, the input is time. This is the position function, the original function. And then it gives you units. And the question's going to ask you for all these different things. And I'm sure when you first looked at the screen, this seemed like, oh no, this is going to be a horrible problem. It's actually going to be fairly easy. And the only work you have to do is to really interpret what each of the questions is saying. If you can translate each of these words into either a first derivative or second derivative, and either plug in or solve an equation, the rest of the math is really a piece of cake. So there's good news. Let's do this first one together. And we'll start with A. What strategy am I going to use, do you think, to find instantaneous velocity when t equals 1? Exactly. Velocity is just a first derivative. And when they tell us t equals 1, it means that I'm going to plug in that number to find the first derivative at a specific point. Here's how I would set my work up. First of all, it's really good practice to translate what they're asking for into mathematical notation. V of 1 means the velocity at time 1. Then we actually do the work. I know from the definition that the velocity function is just the derivative of the position function s. So I take the derivative of the original function, and that's the velocity function, and then the last thing I need to do is just plug in 1. And don't forget units. Anytime you're doing a word problem, you must include units in your answer. And the units for velocity are meters per second. Remember, it's like a slope, so there's always going to be two words. Position is just meters, velocity is meters per second. Acceleration would be meters per second squared. Okay, let's look at B. We have the same given information. Now we're asked about the displacement. If you look at your cheat sheet, the chart of terms, you'll realize that displacement is asking about position. And displacement specifically is asking about how the position has changed. So when you set up your expression, what you're actually going to try and find is the difference in the position over the course of the first 3 seconds. So you would calculate where the particle was at the beginning and where the particle was after 3 seconds, and then subtract the two. That's what displacement means. Listen to that again if you need to and make a note, because it's a word that's going to come up a bunch. If I wanted to abbreviate, what I would say is what I'm trying to find is s of 3 minus s of 0. And what this means is the position at time 3, and then I'm going to subtract the position when it started, and that's going to give me the total change in where the particle was. Once you set it up that way, the rest is a piece of cake. This just means plug in 3 to the original function. This means plug in 0. So at time 0, the particle was 0 meters away from the starting line. At time 3, it was 27 meters. That means the displacement is 27 minus 0. In this case, the displacement is the same thing as s of 3, but in future cases, for example, if you're finding the displacement from time 2 to time 7, you would need to calculate both, so it's good practice to do that. And we can just summarize our answer just like that. Let's move on to C. So in C, we're supposed to find the average velocity. And this was the one that I warned you about when we did those keywords, because average velocity is actually not a derivative. If you remember when we first introduced derivatives, we talked about the difference between a secant line and a tangent line. The derivative function gives you the slope of a tangent line, but average velocity is actually the slope of a secant line. It's the slope of two lines that connect kind of an interval. This bar, this is red V bar. The bar indicates that we're talking about an average, and we're going to use what looks a lot like a slope formula. We're going to take the position at the end, which is at the end of 4 seconds. We're going to subtract the position where the particle started, and then we're going to divide by the total change in time, which is 4 seconds, or just 4 minus 0. So recognize that this really looks like y2 minus y1 and x2 minus x1. That's all that we're doing right here. In order to use this formula to find the average velocity of the first 4 seconds, obviously you need to calculate both of these numbers. The distance at time 0 was 0 meters. We did that in the last problem. At 4 meters, I just plugged into the position graph, the position function, and got a distance of 32 meters. And so now when I put this in, I get 32 meters divided by 4 meters, and that's just because I subtracted the zeros, which is 8, and I'm sorry, it should be seconds on the bottom, so it's 8 meters per second is the average velocity. On to D. D says find the acceleration of the particle when t equals 4. If I translate that into math symbols, I would say I'm going to find the acceleration formula and then I'm going to plug in 4. And I remember from my keywords chart that the acceleration is just the second derivative. So my first step is to find the acceleration formula. And I'm calling it a formula, I really shouldn't. It's a function, and I'm trying to find the equation for the function. It's the second derivative of speed. So I'm actually going to refer back to question A, part A, where I found the first derivative, and I'm just going to take the derivative of that. If you remember, the first derivative looked like this, and so then we take the derivative of that, and we end up with 12 minus 6t as my acceleration. And then I'm going to plug in 4 for time. And notice that we end up with a negative number. Notice also the units. Acceleration units are meters per second squared, or feet per second squared, or whatever is relevant to your problem. But focusing on the negative symbol for a second, thinking about what acceleration means, what does it mean if acceleration is negative? Exactly. It means the velocity is decreasing. In other words, the thing is slowing down. And that's what that negative 12 indicates. Almost there. Let's do E and F. E is where it gets fun. And this is actually the first time where we're actually asking kind of a realistic question. If we have an equation for something like a comet, we want to know basically how is it moving, really. And so let's start with the question at the end here, but then we'll come back and describe the motion. The question at the end says, at what values of t does the particle change directions? So that looks like I'm looking for time. But remember that I said when you're looking for time, you have to do some more reading, because it could be that you're looking for time and you're going to use the original function, or you might be using the position function or the acceleration function. So if I keep reading, it says not just at what values of t, at what time, but at what time does the particle change directions? What does that mean? That's not one that's on your keywords chart, so we're going to have to interpret it a little bit. Changing directions usually means that I'm going one way, let's say forward, and then I stop going that way and go backwards. And so when the particle is moving forward and then turns around to go backwards, the distance of that particle goes from increasing to decreasing. Or we could think of it differently. When you change directions, you stop moving for a second, right? You're moving forward and then you move backwards. If you stop moving, we're talking about the velocity. If you were thinking of increase and decrease, we were also talking about the velocity, because the increase and decrease in the position is how it's changing, and how the position is changing is the velocity graph. So changing directions is the same thing as saying, at what time does the particle stop moving? Because in order to go from moving forward to moving backwards, it has to stop just for a second to change directions. So if we can figure out the time when it stops moving, then we'll have solved this question. Now, moving is a keyword for velocity. So what I'm going to need is I'm going to need to write an equation. And I'm going to need to write an equation where the velocity is set equal to 0. And once I write that equation, I'm going to put an equation on this side. I'm going to solve for t, and that will be my answer. Well, we've already got the velocity equation. We set that up in part A. So the velocity equation was 12t minus 3t squared. And if I make it an equation, this is a quadratic equation. It's pretty easy to solve. we'll start with a GCF, and I'm actually going to take out a negative 3t, and I'm going to switch the order. So just double check for yourself that you understand that negative 3t times t minus 4 is the same as that. Foil it back in if you don't see it right away. Once I've got that factored, I can see there are two solutions. It's when the time is 0 and when the time is at 4 seconds. And make sure we label these. Now, time 0 is probably not relevant. That's when it starts. But it means it's traveling, 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 and at 4 seconds it turns around and starts to go back. To answer the second part, or actually the first part, describe the motion, we would actually want to be a little bit more precise, and this is where we're going to use something a lot like the first derivative test that we've been talking about. If 4 seconds is when the particle turns around, we can test numbers on either side of 4 seconds to check what direction it was moving. So if I plug in 1, for example, into my derivative function, if I plug in 1 right here, this is going to be negative 3 times another negative 3, which is going to be a positive number, which means the derivative before 4 seconds was positive. In other words, the particle was moving away from where it started. And then after 4 seconds, if we test 5 and plug in 5 here, this would be positive 1, this would be negative 15. The derivative is negative, which means it turns around to move back towards where it started. All right, home stretch. F, at what time does the particle start to slow down? Just like the part E, we're looking for a time. And you know by now that just because we're looking for time doesn't necessarily tell us which equation we're going to use. We have to keep reading. In this case, it says at what time does the particle start to slow down? Slowing down means that the velocity is changing. The velocity is getting smaller, which means we care about how the velocity is changing. In other words, we care about the second derivative, which is acceleration. So I'm looking for time, and I'm going to set up an equation with acceleration. The question is, what do I want to set the acceleration equation equal to? Well, slowing down, remember back in part D when we calculated the acceleration at 4 seconds and we got a negative number? That negative number tells me that it's slowing down at 4 seconds. So sometime before 4 seconds, it must have started to slow down. And the second that it starts to slow down is the first time that the acceleration is negative. It's when it turns from positive to negative. So if we're trying to look for that point where the acceleration becomes a negative number for the first time, we actually really just want to solve for when the acceleration equals 0, because that's when it switches from positive to negative, which is when it starts to slow down. So we've already got the acceleration equation. We calculated that back in part D, and it was 12 minus 6t. We set that equal to 0, and then solving for t is very easy. And it turns out the answer is at 2 seconds. At 2 seconds, it starts slowing down. At 4 seconds, it actually stops and turns around. That's it. Use these strategies to work your way through this one. And please do record any questions that you have about this skill. I'm not going to explain this problem, but this is what you're going to work on in class. So I expect you to come to me if there are ones that you don't understand. And that's the end of lecture 4.4a. I know it's been a long one. Thank you for sticking it out. Just double check before you come to class that you're really comfortable with what is the relationship between position, velocity, and acceleration, and that you know how to explain that relationship both when we look at graphs and when we're doing word problems. See you later.